And while Tim is setting up his mic, so Tim O'Shea is our next speaker. I think today in his function as founder of DeepSig, I believe.
Yep.
So
both. Okay.
You'll probably talk about that. Yeah, we're a little bit behind schedule, but we'll just have to let it slip a little. Otherwise, it would be unfair to the speakers. So I'll just give you I'll just signal you when I think you're running out of time, as far as I'm concerned. So yeah, Tim, take it away.
All right. So sorry about the delay there. All right. So I'm going to talk about what I believe is the future of radio, and really signal processing going under kind of a sea change to learned systems rather than kind of heavily analytic models. And so, yeah, I'm here on two capacities. I'm with the Hume Center at Virginia Tech, and I'm also with DeepSig, which is a startup in this area that's looking at kind of maturing these technologies very quickly. All right, so if you look at deep learning, this is not going to be a deep learning tutorial because we don't have enough time. So I'm going to kind of talk about things at a high level. And so if you look at deep learning, there's several kind of really key things that are worth taking away from it, right? So the biggest change here is if you look at on the top here, we have a very large convolutional network that's doing object recognition. The really exciting thing that's happened here is learning systems have moved in this trend towards feature learning, which means that rather than building different features or different transforms on a data set, we can put in kind of a very big, large, raw data set and learn kind of high-level objectives directly from that. And this is called end-to-end learning. And so feature learning and end-to-end learning are really the kind of the key things that are novel and exciting in deep learning. And they go far beyond what we've seen so far in applications of deep learning. So these are really widely applicable to many, many domains. And feature engineering is kind of rapidly becoming irrelevant. So this hasn't happened in radio yet, but if you look at image recognition, there's many different features people used to use, SIFT and bag of words and all these different features, and they're no longer needed because we can do feature learning directly on large data sets to accomplish high-level recognition tasks. Now, the exciting thing about this is that feature engineering actually creates barriers, right? So that's what makes integrating code hard, is that you have all these different models of different algorithms that you have to kind of jam together somehow whenever you're building a big system. And so this is actually really exciting because not only are we learning end-to-end systems, we're able to do so in kind of a uniform architecture, which is great. Okay, so, right. Now, there's a lot of obvious applications of deep learning that are getting a lot of press. And so, we just saw a bunch of stuff launched on the iPhone X yesterday. We have custom chips for object recognition and vision. We have self-driving cars heavily using the technology, and we have voice recognition heavily using the technology. And so these are kind of widely used. They're sort of ships that have already sailed, and they're fields where deep learning has already proven itself to be an extremely mature and powerful capability. And we're seeing custom silicon now to very efficiently implement these. So we're seeing custom processors that are designed with an architecture to mirror the algorithmic architecture. But there's a lot of things still brewing, right? And so there's like an unbelievable number of deep learning applications which have not really seen the attention they deserve yet, and that they have an enormous amount of momentum that's coming along. And so just to kind of mention a few of these, this whole idea of representation learning is to me is one of the most exciting things. And so there's this notion of a thing called an autoencoder. And really what you're doing here is you're jointly learning these two tasks. One is an encoder, one is a decoder. And then you're learning this compressed representation, right? And so this is an unsupervised learning tool where you use a large network, and you're able to just jointly learn this encoder, decoder, and this representation, right? And this is really powerful. And so the first, this is used as a form of nonlinear dimensionality reduction, and it's also used as a form of compression. And so it's really exciting because you really only need a loss function that tells you how good is your reconstructed input based on your original input, and it measures that distance. And based on that, you can optimize both the encoder and the decoder. And the thing that's really exciting about this is, we've had compression algorithms before, But when you minimize this, you're doing it on a data set X here to learn a domain-adapted compression scheme, which is very tailored to the distribution of the data that you're learning on. And so this is really exciting because we can now learn a very heavily tailored compression scheme for basically any sort of data. Now this is starting to see really wide adoption. So new JPEG standards are coming out. We're starting to see image compression. These two images are 0.08 bits per pixel. The one on the left is kind of the old JPEG standard, not JPEG 2000. And on the right, we have basically an autoencoder-based compression standard, right? And so we're going to start to see in image and video. So Netflix is actually rolling out a video compression scheme using the same technology. And so, compression is very rapidly going to the kind of the machine learning approach. There's some other really exciting applications of this. So encryption is one. If you think about it, encryption is really the task of optimizing the reconstruction of this message P at your intended receiver, Bob, while minimizing the reconstruction error or capacity at the eavesdropper, right? And so there's a really cool paper that talks about basically, if you treat encryption as this problem where you're optimizing to reconstruct if you have a key and optimizing to not be able to reconstruct if you don't have a key, you can very rapidly learn these domain-specific kind of encryption sorts of methods. And so this is a really interesting paper in that it shows you how you can use these tools to do kind of unconventional things that you wouldn't really have thought about. So I've been applying this to radio, and I guess kind of an interesting place to start is just estimation, right? So we saw from Andy Walls last night how complex estimation can be. And if you're trying to build synchronizers and all these different channel state estimators, it's a very, very involved process with many, many variables. And the thing about it is that most of those models are derived under very simple channel assumptions. They're derived under Gaussian and non-fading models. And so as complex as they are, they're actually still very simple when you compare them to the real world. And so we looked at this as just, let's treat this as a regression problem on data. And so what we're showing here is basically doing center frequency offset estimation using a learned approach, just supervised learning. And we're looking at all these different delay spreads. So we start to look at more and more delay spread. And what's really interesting here is we show essentially if you compare the map estimator for a CFO to a learned estimator, under an AWGN channel, they're pretty comparable. And honestly, once you get to larger window sizes, the map estimator wins. But if you look under heavy fading conditions, like a bad Rayleigh channel, you actually see a learned approach can drastically outperform a map estimator very quickly, because the map estimator, in this case, wasn't designed for a fading channel, right? And so it's suboptimal. So you're learning to exploit the actual distributions in the data. All right, so there's a lot of really cool work going on in error correction. And this is mostly pointing to other people's work here, but I think it's totally worth mentioning here. If you look at error correction, everything right now seems to be going the LDPC route. But if you look at kind of theoretical results, people seem to kind of respect polar codes as kind of an optimal option, right, in the representation code word space. The problem is we don't have good ways to decode polar codes. And so there's some really, really cool work now showing that if you use neural net-based approximations, you can come up with very efficient polar code decoders, which in fact kind of equal or outperform belief propagation methods at a much lower complexity. So this is really exciting, and we may start to see this really be adopted to help bring down the computational cost of error correction in pretty soon here. All right, so now the core of the work that I'm really going to talk about here is how do we rethink entire communication system, right? So there's this quote from 1948 from Shannon that basically says, reproducing at one point either exactly or approximately a message selected at another point, right? And this is the task of wireless communications, right? This is all we're really trying to do when we build a radio. And so if you think about it, this is really synonymous with an autoencoder. all you're doing is you're taking a message S, and you're trying to reconstruct some estimate for S at the receiver, right? And really, radio is that simple. Everything else was just kind of a lot of things we've done to make it more complicated and think about little bits of the problem in more detail. So really, all of those problems of synchronization, symbol estimation, error correction, those are all kind of these secondary subtasks that we do to try to get to this goal. And it's a lot easier if we don't want to get hung up on all those kind of details. So this actually works really well. So if we treat a wireless system simply as an autoencoder, in this case, we learn an encoder that encodes some message S into a representation. It passes over some channel impairment model, and then it goes through a receiver, which goes back and estimates, which S was sent. Right? So this is a radio transmitter and receiver. So if we do that, we can start to look at the bit error rate performance of the system. And you can start to look at what does it learn, right? So it's actually really interesting to look at some of the constellations that it learns kind of emergently without ever being told what QPSK is. If it's packing 2 bits into 2 symbols, or 1 symbol that's complex in this case, it learns the canonical QPSK constellation here. And now there's a lot of other options. So as soon as you start packing more bits in, it can learn a lot of new constellation types. So in this case, it learns the 16 PSK. In this case, it learns this kind of pentagonal 16 QAM, which is not something that we would typically use. And the capacity, if you look at it, is right up against basically what a PSK with a hard decision Hamming code would give you. So it's it's getting up against what a conventional system would achieve. And this is still a Gaussian channel, so we're not yet exploiting impairments that differ from our model. So this is where our analytic models should still shine. Okay, so we actually do know a lot about radio propagation, and we'd like to be able to leverage some of that. So we have this notion of saliency, and so we basically looked at if you want to learn an entire transmitter and receiver, you have this problem of complexity, right? You have to learn a very complex system of mappings that takes into account all the synchronization and impairments that may happen. And that may not generalize well because it's very complex and has a lot of parameters. And so if we introduce kind of knowledge about propagation models, can we lower that complexity and improve the generalization, right? And so we have this notion here of a radio transformer network where we break this receiver half of the autoencoder into a parameter estimation component, a set of parametric transforms, for instance, applying a center frequency shift or convolving with some inverse channel response. And then we have a discriminative network, which chooses which symbol was sent. And this is great because in our parametric transforms, we can impart the things that we know happen on a physical wireless channel as inverse operations. And then we don't need to learn them, so we've reduced the learning complexity of the task. And if we do this, we can show the systems converge much more quickly. Right, and we can outperform the system without this. Right. Okay. So, and the other thing to mention here is it's really cool because we can train it end to end, right? So we don't need to train a synchronizer and train a symbol detector. We can train the entire thing as one end-to-end task in which it learns both processes because we can differentiate through the entire model, and so it will just follow the gradient all the way to a good solution. Okay, so there's a lot of things we can do with this as a building block, and so I don't get the radio spectrum to myself. I have to share it with all of you, and so we may want to look at the problem of how do you share a channel efficiently, right? And so in this case, we can set up 2 autoencoders where there's basically a mixing process where they receive each other's signals. There's basically interference between different users. And so how do you solve this problem? So traditionally, we come up with some orthogonal scheme, whether it's OFDMA, tiling, or if it's time slotting in a TDMA system. In this case, it learns a pseudo-orthogonal solution. And you can see that in the first order, when you're encoding a single bit for 2 users into one complex symbol, it learns orthogonal BPSK, which is a great solution, they're actually orthogonal, and you get a good result. As soon as you go to more bits and more symbols, now we've learned these kind of offset pseudo-orthogonal QAM or QPSK modes, which is really kind of an interesting solution to the problem. And this becomes really interesting as you start to scale it to more bits per symbol and into larger block codes. And it can start to learn these very large kind of pseudo-orthogonal modulation types. And so here you can see when you pack 4 bits into 8 symbols, you wind up with these kind of very crazy looking pseudo-orthogonal superposition codes here between the two users. And this is exciting. If you actually look at the capacity versus an orthogonal time-slotted system, we're gaining capacity, right? And so this is actually a better solution than kind of just time slotting. All right, so a lot of systems today also incorporate channel state information feedback. And so how can we incorporate that into our learning models, right? And so this is standard in MIMO systems. All of our phones doing LTE will use pre-coding, and so they get some notion of the H matrix, and they pre-code the channel for it. And so we can apply this same principle to learning a MIMO encoding scheme that incorporates CSI feedback. And if we do this, if you look at the diagram, I don't know if my mouse on there. Yeah. Okay, so we can basically learn an embedding process which takes an estimate for the channel state H, and it learns a compact embedding. So in this case, it can learn a 2-bit binary embedding of the channel state, and it can transmit that back to the encoder. And now this is really exciting because the encoder has this arbitrary learned encoding process which gets in an embedding of the channel state, and it gets in the symbols you want to transmit, and then it learns some representation to transmit over the air, right? And then it learns how to recover an estimate for S on the output. So here we're learning a complete MIMO coding scheme with channel state feedback, completely end-to-end, without leveraging anything we would have used before, essentially. And it's really cool to see what this learns. So we're showing at the bottom here, this is the baseline we're comparing to is a zero forcing method for a 2x2 MIMO scheme with perfect CSI without any error correction coding. And then our method here, we're basically showing this is now the fully learned system with a 2-bit CSI feedback. And if you look at the constellations it learns, it's really interesting. So we're learning this quite random looking version of 16 QAM, essentially, that's transmitted on antenna 0 and 1. And then if you look at the received version of these combined with both a diagonal and a kind of uniform channel, you find out in diagonal it looks the same, right? But in a uniform, where kind of you have roughly equal power on each path in H, you wind up receiving this kind of pseudo PSK looking constant power signal. So this is kind of a really interesting scheme that it comes up with completely kind of through gradient descent. And so there's a lot of interesting things we can do with this. It's really interesting from a kind of a privacy perspective as well. Right. So those are kind of the things we've done. And I think it's really exciting because this is kind of a totally new way to think about building comm systems. And it actually works incredibly well without a whole lot of tuning of anything. And I think it's really exciting because there's so much potential and so many open problems and directions to go with this work. And so, right, so we're continuing to work on this at VT and at DeepSig, and we'd love to chat with you about it if you're interested.
You may clap. So Tim, you put us right on track. Thanks a lot for that. But you started late, so I do think this is a very interesting topic. I would like to have at least a couple of questions before we move on. That said, oh, there he is. You can start setting up your laptop. Perfect. All right. So questions. Was there something over there? Where's the mic? Where's the mic man? There we are. Okay. Let's start over there and then.
Hi, Darren. Here. When you're doing this training, what are you using as your training data? Are you using what actually...
Yeah, so there's two answers to that. Sorry.
Where are you?
Yeah, okay. So there's two answers to that. So for learning comm systems, you're there, okay. For learning comm systems, it's actually really great because the problem with deep learning is you need a lot of data. But the great thing is we make the data. And so we can generate synthetically as much as we want in an autoencoder. And as long as we're happy using a simulated channel model, data is free and infinite, essentially. So as soon as you want to do over the air, you need a much more complex test handle to generate as much data as you want. But you can still generate as much as you want. And in this case, you don't have labels, right? So you don't need someone to be labeling it. And so for the learning comm systems thing, you really have as much data as you want.
We have another question here.
I have a couple of questions. When I look at the diagram that you had that you showed at the pattern that it came up with, do both the receiver and the transmitter, I assume, have to know that? And is there information, are you trying to do this in isolation and figure out a better pattern to use, which then both the receiver and the transmitter have to understand? Because
Right.
they can't figure that out as they're going along. I'm assuming
Right.
this is not a dynamic process. And the second part of it is, do you have any intuitive feel for why it came up with that pattern? In other words, is it an anomaly in your channel, or is there something that it's eliciting from the channel that you didn't know about?
Right. So in the case of, so the first question, yeah, you're right. So this is all offline learning. This is something where we're doing communication system design through learning, but we're not doing any kind of online adaptation. And so this problem of how do you update and learn when your nodes can't do error feedback is another problem. And it's interesting, and we're working on that as well, but I didn't show any work to do with that here. But yeah, I mean, if you think about it, we don't modify LTE when we use it. It's already designed in our phones. So we can take one step at a time, and just doing offline design is still a big step, I think.
Jose, you have a question over there? Okay.
Yeah, hey. Over here.
Yeah, go ahead.
Tim Newman,
Go ahead.
How are you? Are you releasing any of this stuff? Is it? I mean, and if so, like, what form is this going to be? Like an out-of-tree module? Are you integrating this into GNU Radio? Like,
So I released my ModRec work a year ago, which has enabled several dozen labs to replicate it. And I'm looking at releasing some of this, but I'm also waiting on journals to be finished. And it will be put out there, but I'm not in a rush to give it away.
Okay, final question is from this side of the stage. I'm over here, Tim, just in case you're wondering.
So I'm wondering how you're contrasting your efforts here with applying deep learning and machine learning techniques with efforts that have been done before with a cognitive radio notion, like there was studies with reinforcement learning. I know also Tom Rando, his PhD dissertation was also artificial intelligence and wireless communication, so it was mainly probably genetic algorithms.
Yep.
So there has been efforts. Is it more like you're focusing on the physical layer while others were on the higher layers? I'm just wondering how to contrast, this new, if I call it wave again, on applying intelligence in the wireless.
So if you look at cognitive radio back in 10 years ago, everything was really an overlay system, right? So we had algorithms, and we're trying to do some kind of a knobs and meters sort of an approach to optimization, where we already have a number of algorithms, and maybe we're optimizing channel access or gain control or mode selection. But it's really kind of this over-the-top optimization. I like to then say the cognitive radio winter occurred, and things kind of tapered off for 10 years while people realized, well, we can do this, but rate selection, we can kind of just do it with an RSSI and a lookup table. So it doesn't really need anything complex to choose. And so there have been some successful applications of cognitive radio, but it hasn't been super pervasive into our physical layer. And so I think the difference is now we can learn these very complex end-to-end systems that are optimized all the way down to the raw sample representation level. And so there are no blocks of expert algorithms in the middle that create integration problems and create blocks that we can't integrate through to optimize, or differentiate through to optimize. And so I think now we have this deep cognitive radio, to create a terrible word, that we don't have these constructs in the way that make optimization difficult. Right? We can just express the basic problem, and now we can deal with optimization tasks that are 2 orders of magnitude larger than what we used to be able to do, and we can just kind of optimize through the whole thing. And that's really the difference between what we can do now and all the cool work that went on 10 years ago.
Thank you, Tim. So our next, go ahead.